Okay, in this unit we're going to talk about something called aromaticity, which in my opinion is one of the most fascinating phenomena in our universe. Though it's something that most people probably have never heard of unless they've actually taken organic chemistry. It turns out this is an extremely important property of many molecules, and it's extremely important to biology, as you'll come to understand. Now, despite the name, aromaticity has nothing to do with smell. In fact, it's actually a chemical phenomenon. And if I had to give sort of a layman's definition, just a simple definition in the beginning, what I might say is that aromaticity is a property that makes molecules unusually stable, and it exists when certain magic numbers of electrons are allowed to exist in a ring. So that may sound a little bit like fantasy, maybe something out of Lord of the Rings perhaps, but in essence it's actually quite accurate and quite sufficient. So you need certain special numbers of electrons, and you'll understand what those numbers are soon enough. And they need to be able to exist in a ring. And if you get that, what you get is an aromatic molecule, and it is unusually stable, which in this context simply means that it is relatively resistant to undergo change, chemical change reactions. Okay, so before we dive in and seek to understand what aromaticity is, I thought that it would be useful for us to look at some examples of aromatic molecules so that you can see where aromaticity occurs and why it's important in real-world context. So the first example that I'd like to point out is one that you may have heard of. In fact, it's benzene. So this is actually sort of the quintessential aromatic molecule. It is what looks like a cyclohexatriene, but in fact it's quite different than that. Now, we're going to talk in very great detail about the chemical properties, the physical properties, and the reactivity of benzene. So where else does aromaticity occur? Well, it turns out, as I noted earlier, that aromaticity is absolutely everywhere in biology. It's actually quite crucial. And so we can look at some very key examples here. So for example, if we look at the 20 major amino acids, which I've shown here, we look a little bit closer, we can see that in fact 4 of them incorporate aromatic rings. And so for example, there's phenylalanine, which I've shown here. And you could sort of see this ring here. This actually looks just like the benzene ring that I just showed. And in fact, it is this is an example of a substituted benzene, but when the benzene is a substituent on a larger molecule, we refer to that substituent as a phenyl, and so this is actually a phenyl substituted alanine, hence the name phenylalanine. The next amino acid right next to it is one called tyrosine, and so you can see that this is has a benzene ring with a hydroxy group coming off of it, and that type of functional group is known as a phenol, right? So it's sort of a phenyl alcohol or a phenol, and tyrosine plays many crucial roles in biology. The next one is the amino acid tryptophan, and again you can see this benzene looking ring, but there's actually a bit more. So if you look at this entire system here, this entire ring system is actually its own aromatic, right? So it's actually, first off, it's an example of a heteroaromatic. Now what that means is that there's an atom within the aromatic ring other than carbon. So it's a heteroatom, it's a heteroaromatic. This is also an example of a fused aromatic, because we actually have 2 different aromatic rings fused together. So we have a normal benzene type of aromatic, and it's fused to this heteroaromatic right here, this 5-membered ring. And so this is an example of a fused aromatic. And then specifically, this exact structure that I've circled in green is called an indole ring. So that's the specific name of that substituent. So tryptophan is an example of an aromatic amino acid with an indole ring incorporated. And then the final one, shown at the bottom here, is the amino acid histidine. Now, this ring right here is also aromatic, and you'll come to understand why that is aromatic, even though it looks quite different than this benzene-looking ring. But it is also an example of a heteroaromatic. In this case, we actually have two different heteroatoms and only 3 carbons, but it is still aromatic. And the specific name of this 2 nitrogen-containing aromatic group is called an imidazole. So histidine contains an imidazole aromatic ring. Okay, we can look at other areas of biology. So if we look at neurochemicals, there's many different kinds of important chemicals that are responsible for the activity of our brain. I've just selected 2 of them to talk about. So the first one is dopamine. So dopamine is very important for many reasons, and one of them is that it's actually the chemical that's responsible for reward. So when you do something and you feel a good feeling for having accomplished something, for example, learning something in organic chemistry, you might get a rush of this chemical dopamine. And the other one that I've shown here is serotonin, so very important neurochemical as well. And this is important for feelings of wakefulness and also well-being. Now, you can see the aromatic rings here. So here, again, this looks like a benzene nucleus, and it actually has 2 hydroxys coming off of it. So this is another example of a phenol, and it actually turns out that this has a more specific name, which is not terribly important that you know, but it's known as a catechol, and that just has 2 hydroxy groups next to each other on the ring. And then over here you might recognize again that this is an indole ring in serotonin. Now if those look familiar, it's for a reason, and actually these neurochemicals are actually produced from the amino acids that we just talked about. So dopamine here is actually synthesized from tyrosine. So tyrosine gets converted to dopamine, and you can see the changes that happen. So we actually add a hydroxy group to the aromatic ring, and then we decarboxylate. We remove that carboxylic acid and we get to dopamine. And for serotonin, tryptophan is the precursor. So tryptophan needs to be hydroxylated and decarboxylated. So same sort of transformation for both of those, and you get these important neurochemicals. Now there are many others that we could talk about, and when you really start to look into these, you see that many of them have related looking structures, and in fact are related in terms of how they're synthesized in the body. So just showing 2 more here. So we have, in this case, we have epinephrine, which you might know better as adrenaline. You can see how closely related it is to dopamine. In fact, it just has an additional hydroxy group. Of course, adrenaline is responsible for that fight or flight response that you get when you have something scary happen or exciting. And then the other one I've shown here is melatonin. So melatonin, you can see, is extremely closely related to serotonin. We've made a methyl ether out of that hydroxy group, and then we've also appended a group onto that amine group here, and we get to melatonin. And so you might know melatonin as being important for the sleep cycle, and in fact serotonin and melatonin are sort of 2 sides of the coin of wakefulness and sleep, sort of your natural biorhythms. And both of these are derived from tryptophan, and so in fact if you are deficient in tryptophan, you can actually have issues related to your sleep cycle, your wake cycle, and also your sense of well-being. So that's actually can be an important dietary supplement for that reason. Okay, well, moving on, one of the most important aspects, of course, of biology is the genetic information, DNA, and I show a very pretty picture here of a portion of the DNA double helix. Of course, everyone knows that the actual letters of the genetic code are the base pairs that are in the inside of that helix. And this is sort of a blow-up top view of a TA and CG pairing. And it just so happens that those base pairs, again, the letters of the DNA, are in fact aromatic rings, right? So we can actually go ahead and look at the chemical structures. And so adenine, guanine, cytosine, thymine, these are all aromatic rings. Now they're very much heteroaromatics, meaning that they contain many heteroatoms, but nevertheless, they are aromatic. And one of the things that we'll come to understand about aromatic rings is that they're planar. So we'll understand why planarity is a key structural feature, but that's actually very crucial to the structure of DNA, which is hopefully fairly obvious, that you've got these planar base pairings within the double helix that can actually stack on top of one another. And you can imagine if you didn't have that planarity, it would be very difficult to have them fit in this nice sort of laddered situation that we see in DNA. And so if you didn't have aromatic base pairs, you would have to have a structure for the genetic code that was just wildly different, and it's actually difficult for us to imagine. There's another aspect of aromaticity that's actually crucial, and it has to do with presumably how life began. And so it turns out that, again, as we'll come to understand in depth, aromatic rings are extremely stable, which means that it's actually a thermodynamic driving force for them to form, right? And so in the prebiotic chemistry on the Earth, all you had was inorganic chemicals. And so somehow you needed a way for those chemicals to form into these base pairs, or presumably something very closely related to these. Now, without a thermodynamic driving force, that's going to be very difficult to do, because you're just going to get random messes of chemicals. But since these are so stable, because they are aromatic rings, this actually serves as a thermodynamic sink. And so those chemicals will sort of spontaneously find their way to these stable structures. And so it's because these form spontaneously from materials that rain down from comets or what have you, that's then the building blocks that life had available to actually begin the process of forming a genetic code and getting life kickstarted. Okay, and there we go, it's circling the aromatic base pairs. Okay, another very important example, particularly for those of you who are thinking of going into medicine, is that many of the pharmaceutical drugs that are available are in fact incorporate aromatic rings. And in fact, aromatic rings are one of the most common building blocks in pharmaceutical design, for many reasons which we can go into later. I've just picked 4 very well-known pharmaceuticals here that you probably have heard the name of. And so here, this first one, Nexium, this is used for acid reflux. Again, you can sort of walk through and see that there's one aromatic ring here. In fact, this is a fused heteroaromatic grouping here. And over here we have another heteroaromatic. This is known as a pyridine group, so we'll talk about that one later. We also have Lipitor. Lipitor, of course, is used for lowering cholesterol. And here we have 4 different aromatic rings. We have 1, 2, 3 benzene-looking aromatic rings. And then here's another heteroaromatic. This is known as a pyrrole. Viagra, I'm sure you know what this one is for. You've seen the commercials. Again, based on aromaticity. So we've got a benzene-looking ring, and then we've certainly got an aromatic ring here. It's another heteroaromatic. And I'll leave open the question to you for now, but maybe you can put some thought into it, of whether this 6-membered portion is also aromatic. So think about why that might be aromatic or why it wouldn't be aromatic. And we can come back to that in class or otherwise. And then finally, here's a very simple pharmaceutical. It's known as Ritalin, treatment for ADHD. And here we've just got a very simple phenyl substituent, but again, aromaticity is part of that drug. Now, I would encourage you, if you're interested, you can go and look at many more available medicines. In fact, here's a website that you could go to to see many of these compounds. So there's these PDF posters that you can look at, and you could just quickly browse through that and see just how prevalent aromatic rings are in pharmaceuticals. Okay, very quickly, we can also think about materials. So materials is a very important aspect to our lives, be that from plastics or more space age types of things with functionality. I could just give two examples of where aromaticity plays a key role. So here's the molecular structure of the polymer known as Kevlar. So many polymers are based on polyamides, right? So this functionality here is an amide, and if you string a bunch of those together, you get polyamides. So nylon is a very famous example of a polyamide. In the case of Kevlar, we've got aromatic rings all through this structure. And again, aromatic rings are planar, they're very strong, and so they give Kevlar this very unique structure, which, as you probably know, is used in bulletproof vests. So aromaticity saving lives here in terms of stopping bullets. And one more example, you might have heard of graphene. It won the Nobel Prize a couple years ago. And this is an example of basically an infinite sheet of aromaticity. And graphene is quite remarkable in that it's extremely highly conductive, and it's also extremely strong. Related materials would be carbon nanotubes or buckyballs, things like that, with very interesting properties. Many people call these the material of the future. So aromaticity is very much integral to the properties of graphene. One final category is dyes, so things that give us the color in our lives. Here's an example of the first synthetic dye. So it used to be that many of these bright colors had to be derived from nature, and certain colors like intense purple were very difficult to find in nature, and so they were very expensive and then thus reserved for royalty. So you would only see purple in royal cloth and clothing. But then in the 19th century, it was figured out how to make synthetic dyes, and the first one was this compound called mauvine, and this is a picture of how wonderfully colored this is. Again, you can see here we've got aromatic rings all through this molecule. In fact, that's the integral structure of mauvine, and we can talk about later why that structure produces such brightly colored compounds. Show one more example. So many dyes are used as food colorings. Here's one that's responsible for green food coloring. It's called fast green FCF, or otherwise known as green number 3. And so there are this sort of core tris phenyl structure that's common to many of these dyes, and then with some various functionality all around that changes the actual absorbance of the color. You might find it interesting to go look at the structures that are responsible for other food dyes. This one, in fact, has been shown to cause cancer in mice, and it's not approved in Europe, but apparently in the United States it is allowed to be put into food, so you might find that interesting. One more example, this one is particularly nice. It's called methylene blue, and again, you can see the aromatic structure right there. It's highly conjugated and also charged, and so that gives it this just absolutely brilliant blue color. It turns out that methylene blue is used as a stain and also as a drug for certain indications. If you're interested, you might YouTube the blue bottle experiment, which is actually sort of a nice color change experiment to see, and it also has to do with oxidation, which is a little bit outside of our topic right now, but it's a nice demonstration to see. And then the final thing I just want to mention is that aromaticity as a electronic property actually shows up in some other circumstances, such as transition states for reactions. Again, let's just remind ourselves that aromaticity is this property of certain magic numbers of electrons allowed to exist in a ring, and so that ring electron situation actually occurs in certain transition states as the molecule is going from starting material to product. And so here's an example where we see a hexatriene undergoes reorganization to form a cyclohexadiene. This is called an electrocyclization, and hopefully we'll have time later in the semester to talk about this. But the key point right now is that there are a certain number of electrons, in this case 6, that are undergoing reorganization within a ring, and that transition state then looks exactly like an aromatic ring, in fact just like a benzene ring. And so this aromaticity equates to stability. And so if you have a transition state that is stabilized by aromaticity, it's going to be the lowest energy transition state for a reaction to proceed through. So that's why the path goes through those aromatic transition states. So that's just something to keep in mind, that aromaticity is also important in transient types of situations like transition states. Okay, so that's just a brief overview of where we find aromaticity in the world. So what we want to do in the subsequent lectures is to understand what is aromaticity. We want to dive into this a little bit more. We also want to understand exactly what causes it, what are the circumstances that give rise to aromaticity, and then especially we want to understand the implications of aromaticity for both the structure of the molecules that possess it and also the reactivity of those molecules. So that's what we'll be looking into in the next lectures.